Welcome to part 4 of lecture 9 on separations. This final part will cover some actinide specific separations. We'll give examples of solvent extraction, ion exchange, and the other methods that we've described previously, those separations for plutonium, americium, and curium. We'll now review some separations for the actinides based upon what we discussed on overall separations. We'll start with plutonium. Separations of plutonium, obviously from the Manhattan Project. Currently there's about 2,000 metric tons of plutonium that have been produced. The current rate's around 75 metric tons a year. The separated amount, we have a little over 200 metric tons for the fuel cycle and 200 metric tons for devices. So those are some of the current situations on separated plutonium. As we discussed earlier, Purex is a large-scale processing route for separation of plutonium. As we gave detail on this separation route in earlier lectures, it will not be covered for the plutonium. The first route for separating out plutonium on a large scale is the bismuth phosphate process. This was done during the Manhattan Project, and you get precipitates of phosphate, of bismuth phosphate, in acid. These precipitates carry tri- and tetravalent actinides. So unlike some of the solvent extraction systems where we get tetravalent and hexavalent metal ions traveling together, in this case we get the trivalent and the tetravalent. So one could form this carrier type process with bismuth nitrate and phosphoric acid. You can then precipitate out the solid, separate it, and then achieve any further separations based upon the exploitation of the chemistry. So for instance, with plutonium could be in the 3 or plus 4 oxidation state. Addition of bismuth nitrate or phosphoric acid will drive the precipitation of bismuth phosphate carrying the plutonium 4, along with any other trivalent or tetravalent metal ions, actinides that are present. The plutonium can then be oxidized to the 6, which would achieve a separation of that material. In some forms of the bismuth phosphate process, sulfuric acid forms uranium sulfate, which prevents precipitation of that material in the solution. So one could use that as a route for trying to tune the chemistry of the uranium so that it does not come out with the plutonium. And this method can be used after initial purification methods. For instance, the lanthanum fluoride precipitation for trivalent, tetravalent actinides can first be used to achieve a separation. Bismuth phosphate can then be used to further purify the material, and then an oxidation of the plutonium achieves a separation of the plutonium in this route. As we've already discussed, solvent extraction, plutonium is well known with tributyl phosphate, part of the Purex process. There's some interest in third phase formation. There's some literature on this and links into the website. Ion exchange and extraction chromatography are also well known for separations of plutonium. These are more laboratory scale separations. Some trends can be based upon oxidation state. So plutonium 3, 4, 5, and 6, imagine they have different oxidation states. And this would be sorption onto a strong base anion exchange resin in HCl. So for instance, the plutonium 3 is not absorbed, and the 4, 5, or 6 are sorbed at different HCl concentrations depending upon their oxidation state. So this could be a route for purifying plutonium by sorbing it to an anion exchanger, reducing it, and upon the reduction to the 3, the plutonium is released. Another example is shown here, where we have some of the different plutonium oxidation states. The plutonium 6 sorption has very high properties on this Dow-X resin, so this would be an anion exchange resin, whereas the 4 also has relatively good sorption properties, but less than the 6. In general, cation exchange trends for plutonium, the nitrates, sulfuric and perchloric acid show stronger influence than the HCl. And there's an increase in distribution coefficients in perchloric at high acidities exhibited for plutonium-3 and plutonium-4. Other separations of plutonium can be based on some of their volatility behavior, like uranium. Plutonium hexafluoride is volatile. This can be a route for separating out plutonium, so producing the fluoride from the dioxide. And then the hexavalent form can be decomposed to the tetravalent form of the fluoride species, which is not volatile. This species can be then removed on this decomposition column. There's also some new work on supercritical fluid extraction. Most research is done with CO2 as a supercritical fluid, but with this supercritical fluid, you have ligands like tributyl phosphate, thionyl trifluoroacetone, and use this to complex plutonium. This has been studied for extraction of plutonium from soils. Okay, this ends the first part of our plutonium lecture. The second part will cover the metals and properties related to nuclear fuel. And some final examples of plutonium separations, reviewing the systems and concepts that we've discussed previously. Alkaline solution chemistry, often not exploited for separations, can be used in plutonium. One would need strong ligands to compete with the hydroxide formation, so fluoride, carbonate, peroxide species of the actinides are certainly known. You can get high stability based upon the higher oxidation states can be achieved with plutonium, and there are also conditions where plutonium-7 can be stabilized, and this compound can be used in this species as a route for separating plutonium from metal ions in a solution. In particular with an alkaline system, is that you can get soluble plutonium species with precipitates of other metal ions. And then finally, a review of what we just discussed with room temperature ionic liquids. There's some quaternary ammonium with anions we've discussed, liquid-liquid extractions as we gave a previous example, and then there's electrodeposition studies, and this is something that's really ongoing and a potential route for forming plutonium metal for both experiment and application purposes. The trivalent metal ions, americium and curium, can also be separated, and we'll describe both those metal ions. Tributyl phosphate separations based on solvent extraction of americium can be achieved. Americium can be extracted from neutral low acid solutions with high nitrate. Also, oxidation of americium to the 6th state will achieve a separation, as we discussed. Nominally trivalent metal ions, and what we discussed previously show that you do not have high solvent extraction. Conditions can be achieved to have the high trivalent metal ion extraction, but with americium one can make the oxidized americium-6, and then that would achieve a separation based upon the fundamental chemistry of the tributyl phosphate that we described in the Purex process. In an example of this work, with 100% tributyl phosphate from 1 molar nitric acid, you get wide separation factors of americium from neodymium. Americium separation from the lanthanides have also been performed using 1 molar ammonium thiocyanate aqueous phase, so a complex in the aqueous phase that helps drive the separation. Dibutyl butylphosphonate has also been used. You get the phosphonate functional group. It's similar to tributyl phosphate, so you get a functional group such as that, but a stronger extractant for americium. And the trialkyl phosphine oxides, as shown here, are also used. Again, one of the differences between the tributyl phosphate and this molecule is that you're missing the oxygen here in this molecule compared to tributyl phosphate. This increase in the basicity of the functionalized part of the molecule has a way of tuning the extractions compared to the tributyl phosphate, the dibutyl butylphosphonate, and the trialkyl phosphine oxides. Americium and curium extract with this ligand in 1 to 2 molar nitric acid, and studies have been shown that you can have 30% of the trialkyl phosphine oxide and kerosene, and then you can extract the trivalent, tetravalent, and hexavalent actinides, and then you can strip out the americium by treating the organic phase with 5.5 molar nitric acid. Other solvent extractions that are used for americium includes hdhp. This is part of the tall-speak process, which you can look at. You can look up in some links on the separations page, and will be part of the separations presentation. Tall-speak uses hdhp, nitric acid, DTPA, and lactic acid. So this organic, the hdhp, is shown here. It goes into the organic phase. The DTPA, diethylene triamine pentacetic acid, remains in the aqueous phase, and lactic acid is used as a buffer. CMPO has also been used, the ligand shown here, and this is part of the Truex process, which is used for fission product extractions. So separation from the lanthanides and actinides from the fission products. And this also employs tributyl phosphate, the CMPO, oxalic acid, lactic acid, again as a buffer, and DTPA. Other extractants that have been evaluated include some amine salts. They've been evaluated in low acid, high nitrate, or chloride solutions. Common extractant is called this aliquot 336, which is shown here. This is useful for extracting in low acid and high salt solutions, and you get an extraction sequence of curium being less than californium, americium, and einsteinium. This has been examined at Argonne National Lab for process separations involving americium, the aliquot 336. There's also a number of amide extractants. The amide functional group is shown here. This is the basis of a process that's been evaluated in Europe called the Diamex process, where this malitamide has been used as part of the Diamex process, and in 3 to 4 molar nitric acids, now we're at higher acid concentrations, you get a selective extraction of americium over neodymium. Other separations have included separations of americium from the lanthanides with an extraction reaction. An example that's shown here is with Cyanex 301. This compound is shown here. This ligand is stable in acid, and as an example shown here, there's distributions of the trivalent americium and the trivalent lanthanides in 1 molar Cyanex. That's around 16 mole percent of Cyanex 301 in heptane. So you can use this ligand to achieve selective separations, and it's driven by the soft donor properties of these ligands. Irradiation studies have also been performed with phosphorus compounds, and extractions start to become problematic at relatively high doses. And this has led to the synthesis and characterization study of other phosphonic acids that tend to be less sensitive to the acid concentration, less sensitive to radiation and hydrolysis effects. However, most of these ligands operate with synergistic extractions, so you tend to have more than one ligand in the solvent system. So, for example, these diphosphonic acids will work with tributyl phosphate, trioctyl phosphine oxide, or tributyl phosphine oxide. The aqueous phases are between 0.1 and 1 molar. So the acidity isn't as high as some of the extractants that we saw on the previous page, but they're in a regime which is relatively easy to control. Separation of americium and curium has been examined with ion exchange, And much of this exploits the fact that lithium chloride has shown to separate the actinides from the lanthanides. As shown here, here's an example of 10 molar lithium chloride separation. Distribution coefficients on Dow-X resin, we see that the lanthanides have a very low distribution coefficients and the actinides a much higher distribution coefficient. So ion exchange has been used in two tracer type levels, one using a displacement complexing chromatography. It involves a two ligand system, two metals that act as competing cations. You use the slight differences in the complexation between americium and curium to achieve a separation. This method is somewhat cumbersome and complex, can be used on a small scale but not particularly suitable to large scale separations. Another route for separating americium, curium, and lanthanides is to sorb the material to a cation exchange resin at pH 2. And separation of curium from americium was achieved by using a relatively weak phosphonic acid solution, this ethylene diamine tetramethylphosphonic acid, at pH 3.4 in 0.1 molar sodium nitrate. And he achieved a separation factor of 1.4. Not a particularly high separation factor, but one that could be used to achieve a separation if enough effort is put into the system. Large-scale gram quantity separation of americium curium has been performed using cation and anion exchange, and it's using ligands such as alpha hydroxy isobutyrate, which we showed was used in the discovery of these elements to separate the lanthanides, and they also are useful in separating the actinides. DTPA can also be used as an organic ligand in this case, where the metal ions are sorbed to the resin and selectively removed with the acids. The LUN can be varied using a gradient of methanol and nitric acid. Best separations were achieved under high pressure. Separation factors can be as great as 400, much larger than the separation factor as we previously discussed. And the use of high pressure increases the theoretical plates of the system, enhancing the separation. Extraction chromatography is also performed with americium. One can think of extraction chromatography as combining solvent extraction and ion exchange, where there's a mobile liquid phase, generally the aqueous phase, and a stationary liquid phase, generally represented as the organic. So for the americium work, you could apply studies that were performed with the organic ligands such as hdhp, CMPO, aliquot 336, and these are the basis of ichrome resins. There are some limitations in the solution depending upon what sort of ligands you have. These are mainly based upon the fact that these ligands will coordinate strongly with the metal ion, preventing interaction with the resin. There is another resin from ichrome which uses ethylhexylmethane diphosphonic acid on an inert support, and this extracts trivalent, tetravalent, and hexavalent actinides. In fact, this resin binds those metal ions so strongly that there's a need to remove the organics from the support in order to liberate the metal ions from the column. There's also variations of support. The ichrome resins are just hydrophobic interactions which keep the resins on the column. One can also covalently bond molecules to silica, and then some of these sites that it can be covalently bonded, you can coat the particles with ferromagnetic make them have ferromagnetic properties, so after separation you can use a magnetic field to separate the resins. You pull out the resins from the solution, thereby separating out any extracted americium. Other aqueous separation processes for americium include precipitation. This is driven by the formation of insoluble americium species, everywhere from trivalent to the pentavalent americium, here shown as the carbonate. Particularly this species, where americium can be oxidized to the +5, where curium cannot be oxidized, is a route for separating americium from curium. Americium can also be separated from the lanthanides by oxalate precipitation, where particularly the use of dimethyl oxalate as a route for this selective method of precipitation to achieve 50% lanthanide rejection, with only 4% americium rejection. So in this case, the precipitate winds up being enriched in the americium. Other routes for precipitation include americium 6, and the precipitation of curium-3. So in this route, the hexavalent state is soluble, where curium, as a trivalent, could be precipitated by such species as the fluoride. There's also pyrochemical processes for separating americium, particularly from plutonium, where if in a molten salt system oxygen is introduced, plutonium dioxide forms and precipitates. And americium can also be partitioned between liquid bismuth or aluminum and molten salts. I think this could be thought of as a solvent extraction system, where the solvents are molten salt and a liquid metal. Distribution coefficients of 2 for the aluminum system have been achieved for americium. Volatility-based separations of americium from plutonium can also be achieved by exploiting the the plutonium hexafluoride, which is volatile. So the formation of this fluoride species in a fluoride salt. So you start with the tetrafluoride of plutonium, bring it to the hexafluoride state, and achieve separation from americium by the volatilization of the plutonium species. Curium separations are very similar to what we've already described for americium. So this is just a review. Again, tributyl phosphate can be used, not at the high acid concentrations that are useful for plutonium and uranium, but at lower acid concentrations. hdhp can be used in nitric and lithium chloride systems. CMPO, curium can be treated similar to what was described for the americium. Ion exchange, again with the lithium chloride, nitric, and HCl systems, where this work exploits the formation of anionic chloride species at the high lithium chloride concentrations. And then precipitations, particularly from americium, can be used by the fact of precipitating out the americium-5 carbonate species. And then any sort of purification based upon precipitation of curium can be done with hydroxide, oxalates, or fluoride, similar to the conditions that were described for trivalent americium. This concludes our lecture on separations. We reviewed a number of different strategies: solvent extraction, ion exchange, volatility, electrochemistry. From this initial study, one should be able to understand how oxidation states influence different separation methods, different mechanisms involved in solvent extraction, and then some discussion about specific actinide separations, which we just went over. You should be able to describe components of ion exchange resins and, for instance, provide a separation. For example, if one was asked how would one separate americium from neptunium and uranium, one could achieve that separation and should be able to describe it based upon what we've presented, or additionally find out where the information is to get more details. Some questions that one should be able to answer based upon the lecture is: describe the components and concepts of solvent extraction, have some discussion about third phase formation in solvent extraction, and describe a volatility-based separation for plutonium. When you've completed this lecture, please respond to the Lecture 9 PDF quiz and provide a comment on the blog.